Alright, before we get started with the actual lesson, let's spend a minute just to discuss the next few weeks and the idea of where we're gonna be at. If you have this worksheet in front of you from the beginning of the year, take it out. All it is the outline of the whole year with concepts. Okay, if you have it in front of you, or if you have it in your books, take it out. If not, you can just listen for now. So, the spot we're at now is right around concept 50. We're actually on concept 50 today. In the next few weeks, what I'd like to do is go in a specific order here. And the reason being is because of the SAT coming up. So, with that said, your block of assessments from 48 is always blocked off to 53 if you look in your actual worksheet or in your outline for the year. I moved 53 down to the next section. Okay, that's the first thing you'll notice. So 53 was up here in this block. I moved it down to the next section. So it's going to be grouped with the other stuff. In addition, what I've done is I've kind of ignored 52. The reason why, just so you have an idea, after teaching calculus this year, for me, I noticed that you don't do much, if anything, with cube root functions as far as graphing goes. So I eliminated the graphing part for cube root functions. Doesn't mean it's not important. It's useful, and you'll definitely use it in math. But as far as it goes for your SAT, and if you go on to take pre-calculus and you want to take calculus in college, you're not going to use it that often. Okay? So it's not worth spending an entire class period on it, especially with the time that we have. Now, after 51, we would normally go to 52, which obviously I crossed off. Then we would go to 53. What I'm going to do, though, after 51 is actually jump down to 61 and do this section first. Then we're going to come back and do what's in this section afterward. The reason being is we want to get this part done before the SAT. Because there's a lot of stuff with random probability in the SAT, if you've noticed, if you look at the old tests. You'll see some stuff quickly with conic sections, not too much on the SAT. Basic stuff like circles. But generally, these four are really important for the SAT. So I'm going to go to here next, after we finish up concept 50. 50 and 51. Then we're going to go on to this section. We're going to go back here. And notice I've crossed off graphing logarithms and determining the functions here. Those are two topics that we're not going to cover. After that, we're going to go back on track up to concept 68 and see how much we can get done after that. Okay, so just to give you an outline. So we're going to do 50 today. We're going to do 50. It's pretty much going to be today and tomorrow for 50. It's a long concept. We're going to do 51 in one day. Wednesday, keep in mind you have the junior field trip, so we don't have anything on Wednesday as far as class goes. So this will be today and tomorrow. 51 will be on Thursday. Then after these four concepts, we're going to have like a mini test. It's not going to be a long test. There's only four concepts. Okay, so we'll have an assessment on those tests next week. Maybe on let's see, you work on Monday, right, next week? So we'll do like a review on Tuesday, test on Wednesday next week. After that, we'll touch upon the probability. We're only going to do basic stuff here, whatever's covered on the SAT. Because you can do a lot more with probability and statistics next year if you take probability and statistics as a class, okay, which is the other class besides pre-calculus. So we'll touch upon this, look at all the major stuff that's going to be hit on the SAT, do a bunch of example problems from the SAT and stuff. Once we get through all that material, it'll be around like May 5th, that's when the SAT is. Then we'll come back and look at this stuff for maybe like 2 weeks in May, and then we'll have like a week or two at most to take a look at all the stuff with trigonometry. Now, we're going to mainly focus on the first four. Those are the ones that we really want to get through this year. The stuff that you're going to really look at next year in pre-calculus is all of this, but I want to make sure that we look at these four to start. And all this other stuff, you'll be covered in pre-calculus. You're taking. If you go on and take statistics, you're not going to do too much with trig, okay, with sines and cosines, but just to give you a little preview. So I know it's a little bit, discombobulated, but if you want to write it down, we're doing 50, then 51, then we're going to jump and do 61 through 66. Did she sneeze and it went everywhere?
No.
It tripped all the way. That's funnier than that. So 50, 51, then we'll jump to 61 through 66. Then we'll look at the middle section between 53 and 59. Okay, so it's going to be a little bit back and forth, just to give you a heads up. So the numbers are not going to be consecutive. I'm only doing this because of the fact that we're a little bit behind where I want it to be for SAT stuff. okay? All the material that'll be covered. And then after that, we'll get back on track and do 68 onward. Okay, mostly we're going to look at 68 through 71. That's going to be our focal point. Hopefully we'll get to some of the other stuff. If you had me last year in geometry, I know for a fact that I went over these three actually: law of sines, law of cosines, and area of a triangle. I think Mr. Malchek actually got to this as well last year. Okay, and it's not SOHCAHTOA. It's not just SOHCAHTOA. It's a lot more than just SOHCAHTOA. This was, if you remember, this was A over sine A equals B over sine B and stuff like that. This was, C squared equals B squared plus A squared minus 2BC cosine A. Was a weird formula. Okay, but you probably touched upon it last year, okay? Again, it's mainly pre-calculus topics. So just to give you an idea of where we are at as a class right now. Get rid of this last one here. Yeah, get rid of this. This does this, I don't know. Okay. So what we're going to do today is take a look at concept 50. And this is going to be a 2-day concept, I'll tell you right now. Okay, simply because there are a lot of examples, and there's a lot of room for common mistakes in these problems. So I want to make sure that we clear those up. So concept 50 is going to be titled Operations with Rational Exponents. Okay, operations with rational exponents. We have to start by thinking to ourselves first. What did that word rational actually mean? When we looked at that topic of rational functions, what did rational mean it had? A real number. Okay, numbers are real, sure, good. Rational numbers are real numbers, absolutely. Rational number, or rational terms, or rational expressions. Rational is a synonym for what other word, though? Okay, proportion is a nice way to think about it. Proportion has an equal sign.
Oh, a part of it.
A part of it, okay. So what was the other word you just used besides that, a part of it?
Also proportion.
Okay. So a rational exponent just means that there's a fraction in the exponent. Remember, so please write that down because a lot of you seem to be confusing this still. When we looked at rational functions in the last several topics, they had a numerator and a denominator. It was the stuff with like x cubed plus 2x over x minus 3. It was the functions where they had fractions in them. So whenever you see the word rational, I want you to think about fraction. So again, rational and fraction, rational and fraction. So let's go through examples. We're starting with the first example. So operations. Operations means like raising a power to a power, or multiplying two things to the same power, or dividing them. So we're going to go through all those operations again, but we're going to then hit on the point the fact that there is a fraction in the exponent. Okay, there's again a fraction in the exponent. So let's start with the first example. What if we have 16 to the 1/4 power times 16 to the 1/2 power? It's going to be our first example for us. 16 to the 1/4 times 16 to the 1/2. Whenever I multiply two things with the same base, what must I do to the exponents? Add it, right? Where did that rule come from? Remember the rule we had? We said like, yes, it was very basic. X to the 3rd times x to the 4th is just x to the 7th, right? Wasn't that one of the rules that we did?
Yep.
It's the same problem. Now instead of x, I have 16. And instead of a 3 and a 4 as powers, I've got 1/4 and 1/2. So it just looks a lot more complicated. But this rule that we just applied here, where you add the 3 and the 4 together to get the 7, is the exact same thing here. There's no difference whatsoever. Again, don't let it confuse you. People get confused because they see the fractions and they're like, what do I do? I don't know what to do. Oh, it's the same thing. You just add them, right? Just add them up. So I want to add up a 4th and I want to add up a 1/2, right? That's what I'm adding, really? So on the side, I can show the work if I'd like to. If you want to do it in your head, you can. That's fine. Okay? But I can show the work on the side because it's going to make it a little more complicated later. Let's show the work for the first one. Here, how do I add fractions? What do they have to have the same?
Same denominator.
Denominator. So shouldn't I multiply this one by 2 over 2?
Yeah.
Because now this becomes 1/4 plus 2/4. And that makes sense. Because wasn't this a 1/2 before? And isn't 2/4 really a 1/2? I'm just writing it differently. 2/4 and a half, those are identical. What's 1/4 plus 2/4? 3/4. So this number, or this answer, just becomes 16 to the 3/4. And the easy way to think about this, especially when it's in quarters, think about money, right? You've got a half a dollar with the 1/2. You've got a quarter with the other quarter. Half is 50 cents. A quarter is 25. 50 plus 25 is 75 cents. Wasn't that just 3/4? 75 cents in your hands. How many quarters do you have? You have 3/4. That's where this exponent comes in, really. Right?
Is it possible to have decimal as an exponent? Like, it doesn't
Absolutely. And that's what this is, really, if you think about it. Because this is really like 16 to the 0.75. Isn't that what it is, really? Now, the tough part is that it's difficult for me to evaluate it like this. But if I see it like this, I can now rewrite it with radicals and roots and indexes like we did last time. So I can take this, and if you remember, I could write it as the 4th root of 16 to the 3rd power. Remember how we did this last class, and it was before break. So think back for a while back now. I take this denominator, and the denominator becomes my index. The numerator over here, that becomes my exponent. I switched my shapes. I shouldn't have done that. Okay, again, the denominator becomes the index. The numerator becomes the exponent. And now it makes this problem a whole lot easier. Because I can figure out what the 4th root of 16 is. What number times itself 4 times gives me 16? 2. Thank you, Eddie, for raising your hand. It is 2. So this value inside of here is really 2. So this is really just 2 to the 3rd. And what's 2 to the 3rd, though?
8.
Why?
Since 2 times 2 is 4.
Good. It's 2 times 2 is 4, times another 2 gives me the 8. So this turns out to be just simply 8 as an answer. Pretty easy, right? Now, if we started at the beginning here, and just went ahead and actually looked at this, Melissa, is what you're going to say?
Yeah.
What is 16 to the 1/4 really?
Well, the other, you want me to say it the other way?
Or this way too, sure.
Well, I just knew that there were 4 answers, so then I'm 2, and then the other one is 2 of them.
Which is?
4.
Good.
4 times 2 is
Very good. So what Melissa's noticing is she could have said, well, why don't we just break this up? The 4th root of 16 times the square root of 16. That's what it really is right there. The 4th root of 16 is 2. The square root of 16 is 4. What's 2 times 4? 8. Okay, the same answer. Now, that happens to work this time, and I wanted to show you that because there's numerical parts, right? But when these are variables like x's and y's, it doesn't work that way. I mean, it won't work as easily as that. You can't just simplify that easily. Now, here's another thing to try. Go ahead to your calculator, type in the original expression. And if you go back and look, the original expression is simply 16 caret 1/4 times, I'm typing in the code that you would put in your calculator, 16 caret 1/2. Whenever there are numbers here, you're always welcome to go ahead and try it that way first. Okay, you could always do that. You'll see, you'll still get 8. I mean, it's the same exact answer. It should be. You still need to get that same answer of 8. Okay, 2 times 4 that we got up here was still that answer of 8 from earlier. Do it all in one. So, when I type in, it's like opening a bag of chips in a movie theater, right? Come on. Is that the most annoying thing? So, to do, not handing.
No, just
Turn
say
my
it.
words on me.
Just say it.
So when you multiply these two in the calculator, you'll get 8 as well. Okay, again, this is not going to help you though if you have variables. If you have numbers, sure, you can go ahead and type in your calculator. But when you have variables, there's nothing you can do. So you have to know what your rules actually are. Let's look at another example of this. Let's try that again. All right, what if we have 8 times 8 to the negative 1/3? Speculate what you might do here. Good. So Andy's already thinking that, yeah, this exponent is really 1/1. Absolutely. Because it's 8 to the 1 by itself. So start, let me actually use a different color to show that. So the problem starts like this. We start by putting it as 1/1. But now if I want to combine these, I need to add the exponents by But I can't add 1 over 1 and negative 1 over 3. What do I need to get if I want to add fractions? Good, common denominator. So I'm doing again, 1 over 1 plus negative 1 over 3. That's what I'm really doing right now in my head. Whenever I multiply, if my bases are identical, I need to add my exponents. But I can't add this, again, because of the 1 over 1. So Karen said, well, let's just make it 3 over 3 instead. So let's multiply this by 3, multiply this by 3. You get 3 over 3 plus negative 1 over 3. So I'm doing all this work on the side. Remember, this is not really in my answer. This is just the exponent work I'm doing all on the side. So I wanted to add this 1 over 1 together with this negative 1/3. That's what I'm showing you here. What do you get when you add those two numbers together?
2 over 3.
Very good. Again, 3 over 3 plus a negative 1 over 3 is like I'm subtracting, really. Okay, so 2/3. So this actually results to give me 8 to the 2/3. All right, great. 8 to the 2/3, easy enough. What's the other form that I can write this in so I can actually get an answer? In radical form. Very good, Kelly. So square root form. So Mariana, tell me, in square root form, what would this one look like?
It's like the 8 is in the square root of 3 is on like the outside, and then plus the
All right. Absolutely right. Let's make sure we know how to say it. So let's go through this, how to say this. How would I say this? Can anybody actually help me here? How would I say this from beginning to end? How do I make a mathematical statement about that?
Would it be in index of 3 radical 8 to the second?
That's one way of saying it. Absolutely. Index of 3 with the radicand is 8 to the second power. What's another way of saying it? Might be an easier way to say it. Be careful, because that would be if the 3 was out in the front. Absolutely, Nuwan. If the 3 was a coefficient, it would be. Why is that? What else? What else? What if I just had a radical by itself? Wouldn't I say square root? Isn't that what a radical is? Isn't a square root? What kind of root is this? You don't call it 3 square root. You just call it a third root. So the way you would say this, you could say cube root. That's another way of saying it. I would say the third root of 8 squared. Or the third root of 8 to the second power. That's fine also. But we got to know how to say this stuff, okay? Again, third root, that's the 3. The third root of 8 to the second power. What's the third root of 8? 2. Why, Karen? Good. It says what number 3 times multiplying itself gives you 8? Well, that's just 2. Well, I still have this 2 on the outside, right? I got to bring that down. What's 2 to the second power? 4. That's our answer. Now, please go ahead and check. Go back to the beginning. Type this in just like you see it in the calculator. So type it in as 8 times 8 caret negative 1/3. Go ahead and type that into the calculator and make sure that you get 4 as your answer there. 8 times 8 to the negative 1/3. So try typing in our given function, 8 times 8 to the negative 1/3 in your calculator, and make sure that you do end up getting 4 as your answer. So you can always check these. Now, seriously guys, in the SAT, do it on your calculator. Don't show all the work. It saves you time. How do you think people get 800s in the SAT and get these high scores? Because they're able to go through the test so quickly. So use your calculator. When I took the SAT, I had a calculator too. I mean, they weren't the nice ones you guys have now, but they were basic calculators. And if anything was simple enough to just type it in, I always typed it in to make it easier, provided you know how to do it the right way. Like, if you forget these parentheses here around the negative 1/3, you'll get a completely wrong answer. And there's a good chance that will be one of the other choices there. Okay? So if you have this kind of a scenario and it's multiple choice, and you don't need to show work, even on my test, just type it in. I don't mind. You probably won't have that for multiple choice. That's a little bit easier. Just type it in. But in case you did, it's good to know. All right, let's look at the third one. Let's take a look at this problem. Now, this is example 3. We're going to get through about 6 of them today and then another 6 or so tomorrow. So for a problem like this, what do you notice right away? What's one thing that points out, that sticks out to you? Any key points? Okay, there's a major exponent of 2. We got to worry about that right away. Absolutely. I agree with that. What else?
There's 2 different numbers.
Good, Karen. Very good. So say that again. What are they? They're not numbers. What do we call those things? Bases. Very good. They are numbers, actually. That's true. Sorry. Mathematically speaking, we call those the bases. The bases are not the same. The bases are not the same. So we can't just add exponents together again. Remember last time when we said x to the 3rd times x to the 4th is x to the 7th, right? We did that because everything was x. But what if it was... I can't combine anything. There's no way to simplify that because x and y are 2 different things. They don't have the same base. So I cannot add exponents. So I cannot start this problem by simply adding exponents together because the 5 and the 4 are very, very different things. But I see that there's a 2 on the outside. If I had given you a problem last week, and you would all be able to do this one, and it was like that. How do I raise a power to a power? What do I do to those powers? You multiply them. So this would become x to the 12th, y to the 6th, right? I would distribute the 2 to both of these and multiply them. And we did that last week, or a week and a half ago now. Okay, that was easy. But now I have a power that's a fraction. There's no different rule at all here. Different bases, different exponents. I distributed the 2. Do the same thing over here. So we need to multiply both of those fractions by 2. That's really what's going on now. Okay, again, we're raising a power to a power. So here's what I see. I see this as 5 to the 1/2 times 2 times 4 to the 2/3 times 2. That's what I'm seeing this as right now. By taking that 2 on the outside and distributing it by multiplication to each of the 2 exponents. How do you multiply fractions? Because when we add a fraction, we need a common denominator, right? What about when we multiply fractions together? Well, let's just say multiply across. Of course, multiplying is an equation, right? Again, let's multiply across. So this is really 2 over 1. This is really 2 over 1. And now just multiply through the 5. What does this exponent become? 2 over 2, doesn't it? Again, take a look here. The exponent here is going to become 2 when you multiply these over 2. But what's 2 over 2?
1.
So it's just 5 to the 1, really. Again, I know you multiply and you're going to get 2 over 2. This will become 2 over 2. But 2 over 2 is just 1, so write it that way. You don't even need the 1, really, because 5 to the 1 is just 5. Next, when I multiply these together, I'm going to get 2 times 2 up top, which is over. Very good, 4/3. Again, because this 2 times 2 gives you the 4, 3 times 1 gives you the 3. Now, at this point in time, a lot of people then try to add the exponents. You still can't. Why can't I add the exponents still? Good. They don't have the same basis. The property is only viable or valuable here, or credible or usable, whatever term you want to call it here, if the bases are identical. So there's not much more I can do with this. I can write it in radical form like we did last time to see if we can reduce this. The 5 is still simply 5. Then this is going to become the 3rd root of 4 to the 4th. Again, that's what I would have here. This 3 becomes my index, this 4 becomes my power. But I can't go any further, actually, still, because there is no 3rd root of 4. Try and find the number that multiplies to give you 4 when you multiply it 3 times. It doesn't work. 1 by 1 by 1 is 1. 2 by 2 by 2 is 8. I've passed 4 already, so 4 is not going to work for me at all. So at this point in time, either this is my answer, and you could drop the 1 if you'd like to, it doesn't matter, with this as 4/3, or this is my answer. And again, it does not matter which one is right and which one is wrong here, or which representation you choose. They're both correct. It's a matter of which choice is there on the SAT, or which choice is there on a multiple choice.
So, what if it was at 8 instead of 4?
Absolutely, because there is a cube root of 8, right? If this, guys, so we'll stop here with this problem, but hypothetically, had this been an 8, as Andy just said, great question. Because the cube root of 8 is really just 2. 2 to the 4th is 16, and then you do 16 times 5 like any other problem, and you get 80 there. Okay?
No.
Again, it's not 8 though, so we can't do that, but had it been, it might help. Now, This is one of those examples where it doesn't help you to type that in your calculator. Everybody, please, type this in your calculator. You're going to get a decimal value. You're going to get a decimal value. Try it. Try 5 to the 1/2 times 4 to the 2/3, get an answer, and then square the whole thing. You're going to get some random decimal that'll go on forever. A decimal that is irrational. And it won't be one of your choices on your SAT. The choices that are there will be the radical forms that we're looking at now. Okay, again, what did you end up getting for this? Anybody do it? 31 point something? Yeah. And if you do this here, you're going to get around, you'll get the exact same answer. You will. But if it's multiple choice, you're not going to know. You have to sit there and try every single choice to see which one it matches up with. You know what I mean? Okay? So again, it's important to know how the rules work. Let's look at an example that's a little bit more complicated. So we start and take a look, we say, all right, the bases are not the same. One is a 4 and one is a 32, right? So I can't just add exponents anymore. So what did we do in the last problem?
Bring it down.
Okay.
Multiply.
Exponent. Good. So we're going to multiply that negative 1/5 to both exponents. Okay, causing one of them to become negative and the other one to become back to positive. So let's do that. Now this is where it's going to get a little bit tricky. So we've really got 4 to the 5th times negative 1/5 times the quantity 32 to the negative 4th times negative 1/5. That's what's really going on right now. We have to take that negative 1/5 that's on the outside and distribute it to both of my exponents.
Oh,
Tricky. What do we get?
I got 4 to the
Yeah, it is 4 to the negative 1. Well done. Because this is really 5 over 1, right? Isn't this over 1 and isn't this really over 1? These 5's canceled, and you got negative 1 over 1, which is just negative 1 there.
and then times 32 to the 4
Positive or negative?
positive.
Very good, because it's negative times a negative there. Again, take a look. Look at your multiplication of fractions. Negative 4 times negative 1 is positive 4. 1 times 5 is positive 5. That's where the 4/5 comes from. On the left side, reduce the 5's to start, and you have the negative 1 over 1, which is just negative 1. Okay, but this problem is actually a little bit easier to keep going, because we can do further. We can do more work with this. So let's bring it up top.
And then
How can I rewrite the 32?
5.
Fifth root.
5th root. 32. And then
So the 5th root of 32 to the 4th. The 5th root of 32 to the 4th. I start by rewriting that one. Go ahead, Andy. Keep going.
And then break it down to 2.
Good. The 5th root of 32 is 2.
And then exponent 4 is 16.
Absolutely. Well done. There's one more step still.
And then you multiply the 16 and the 4, and then the negative 1, you get the exponent.
Careful. You got it all right to that point. Careful. What does a negative exponent mean? What do I do to it?
Oh, make it a negative.
a fraction, you put it in one.
You move it down to the bottom, or a fraction. Very good. And you make it what instead of negative? Positive. Okay, again. So at this point in time, your next line should say 16 over 4 to the 1. Again, this is currently, I'm going to go step by step. That's one line, that's the next line, that's the next line, that's the next line. In this line here, this is really over 1. It's really over 1. And whenever you have a negative exponent, remember, you move it and make it positive. So I move the 4 to the negative 1 to the bottom, make it positive. But what's 4 to the 1? Just 4. What's 16 divided by 4? Okay? Now if you go ahead and type in this original problem over here, in your calculator, you will get 4 as your answer. Okay, that is a good way to check it. You're going to get 4 here because it did reduce. That part did reduce there. 2 more to go, and I'll let you guys get started in homework. All right, the next one. Let's take a look at an example with all variables now, all variables. So, we've got a problem now with no longer any numbers, okay, all variables.
Why are you laughing?
So, your instructions here will just say, simplify as far as possible, or simplify the following expression, or perform the indicated operation as simplified. Okay, any of those instructions are fine. So clearly, I'm going to see that I have some bases that are the same, but they're around parentheses, right? So within this parentheses set, the first parentheses, are these bases the same?
No.
No. Within the second, are they the same? So I can't do anything to start, so I got to start by distributing the powers. And then maybe I can do something with the exponents. Over here, how do I write this?
So,
1/2, go ahead.
y 3 times half.
Okay, awesome. Somebody else, the other half?
That would
Okay. Just let me okay, it's x times 1/3.
x1
Yeah,
1, yeah, times
that's fine.
and y negative, what, y to the, yeah, that, and so times 1/3.
Okay, that's what I should have on my paper right now. Again, all you're doing is distributing that exponent. Whatever's in the major exponent on the outside is being distributed to each of the inside parts. Now you have to perform the math. That's the hard part, I guess. What is half of 2? 1, isn't it? So this is just x to the 1. Because that's what it says. I see half of 2. Okay, next, I put this 3 over 1, really, and now multiply across. What do I get? Good. Y to the 3 halves. Again, 3 by 1 is 3. 1 by 2 is 2. Next. Good. The 1 has no effect on the problem. It's just 1/3. And finally, y to the... All right. Now that I've gotten rid of all my parentheses, and I've gotten rid of my exponents, at this point in time, now look for common bases. And you can see clearly you have them, right? You got this one and this one together, don't they? And then you've got this one with this one. So let's analyze them separately. Let's start first. Melody, help me out with this one for the x's. When I see this x here and this x here, I want to add the 1 and the 1/3 together. But I can't just add 1 and 1/3. What do I have to have again? Good. So what should I make the 1? Instead of 1, what should I make it? Good. And then once I have that, I want the same denominator, which is? Good. So I make the top and the bottom. Well done. So I get 3/3 plus 1/3. And think about it logically, guys. You're taking 1 plus 1/3. 1 is 3/3. 3/3 is 1. They're synonymous for one another. Okay, 3/3 is just 1. So these two values add up to be 4/3. That's my x component. That's the x work that I have to do. So my answer I'm going to get, and I'll put this at the bottom for the x part, the x is going to be x to the 4/3. That part's done. Now what about the y's? What about the y's? I need a common denominator, right? Clearly? What's the denominator going to be between the 1/3 and the 3 halves? 6. 6, always. Okay. So here, now I want to do this 3 halves plus this negative 1/3. What's missing on the left-hand side to make it a 6? 3. So let's do 3 over 3. What's missing on the right-hand side? just a 2, be careful there. You could say negative 2 over negative 2, but it's not going to help you in the process. It's negative 2 over 2. Because now it's still 6 in time, right? So this becomes 9 over 6 plus negative 2 over 6. What's 9 plus negative 2? 7. Over now. So your answer here is y to the 7 6. Yes. X to the 4 thirds. We had a 1. We needed to add together with a 1/3. We did that work in the upper right. 1 plus 1/3. Instead of 1, we write it as 3/3. 3/3 plus 1/3 gives you the 4 thirds. Now keep in mind, guys, this example and this answer is fine. What's another way I could have written this as a final answer in radical form now? Who can step me through the whole thing and say it the right way, please? How can I write that in radical form with the correct vocabulary?
This is 3 roots in.
I'll hold the chart. Okay, it's, put your parentheses first. Index of 3, square root, the x.
Be careful with the square root because it's a cube root, really, because it's a 3.
Cube root of x, to the 4 times index of 6.
So the 6th root, right?
Yeah, 6 root of y to the 7.
Hold on. Okay? So the 6th root and the cube root there. Now, remember, cube root is a fancy word for third root. This is the third root, just like a square root is really the second root. Okay, square root, second root. Why do we use square root? What's the area of a square? What's the area of a square?
I know this.
Geometry?
Times width.
But if it's a square, that's a rectangle.
Oh, that's like L times
Yeah, L times L, or side squared, right? The term squared comes from the fact that the area of a square is let's go through this fast. If I call this L and W for a rectangle, the area is 9 times width, right? But for a square, when it's the same, isn't the area just side squared? Side squared. Squared is the area, hence the name square. Square comes about from multiplying two of the same things. So when I talk about like a square root, that's really the square root of x, because it's a 2. It has to do with that 2, and that's where the square comes from, the term. From math background. Karen? So, anyway, the point we're trying to get across is that either of these answers are acceptable. Come on, guys. Either of them are acceptable. This one up here, or rewritten in radical form. It's up to you completely to decide. Okay? If you're taking this test and it's a multiple choice, you got to think about what you have to do there. All right, last one. This problem here, let's take a look at it. What's going on with this problem, first of all? A lot, okay, a lot is going on, sure. A lot is definitely going on here. What am I doing though? Am I multiplying things still? Dividing, right? Yes. And what's my rule for division? What do I do to the exponents? Good. We're good. Very good. We subtract the exponents. Remember, in case you forgot. Okay, remember that on the side, random numbers picked. X to the 8th, X to the 5th becomes X to the 3rd. I did 8 minus 5 giving me the 3rd. We talked about that in class. Now, so I need to subtract these now, don't I? So I need to look at the x's and say I have to subtract this exponent minus this exponent. That's what I have to start with. Then I have to look at the y's and say I have to subtract this exponent minus this exponent. But what about this 3 over 9? What's 3 over 9? 1/3. So just start by reducing that, please. So in your answer, let's put a 1/3 out front. Okay, the 1 probably won't even matter, actually, right? We'll drop that 1 probably in the end. All right, so to work on the x components, we want to do 1/2 minus 2/3. That's what we're doing here. Again, I'm doing all my work for my exponents on the side. It's part of my answer, but I'm doing it on the side. So it's the 1/2 here minus the 2/3 there. Common denominator is 6. So 3 by 3 on this side, 2 by 2 on this side. I end up with 3 over 6 minus 4 over 6. What do I get?
1. Negative 1.
Negative 1 over 6. All right, that's great. Negative 1 over 6. So I have x to the negative 1 over 6. Okay, there's my answer for that part. What about the y part? I got to do 1/3 minus 1/4, right? 1/3 minus 1/4. Common denominator?
12.
So I'm missing a 4 by 4 over here and a 3 over 3 over here. This is going to become 4 over 12 minus 3 over 12, which is 1 over 12. So this is y to the 1 over 12.
How come we put above in the numerator?
Now, whenever I divide two things, like I did here earlier, look back up here on the right, upper right part of the page. When I divided these, wasn't this really x cubed over 1?
Yeah.
You asked the question, focus. X to the 8th over x to the 5th. 8 minus 5 is 3, and I leave the third up top. I leave it over 1. So here, when I get my answers, when I subtract these two, I leave them up top for now. But notice, isn't that a negative exponent?
So you're going to take that down anyway.
Good, I'm going to move it down now, but as a
As a positive.
positive. So this becomes, the 1 doesn't matter really. I've got the y to the 1/12 up top, and in the bottom I've got
3x negative 1 over 6.
No one.
I mean positive 1, yeah.
Yes, thank you. Positive, okay, positive.
I have a question. Why did you write x to the 8th, x to the 5th?
That was just a little rule in case people forgot. In case you forgot the rule of division, knowing that 8 minus 5 gives you that 3, that's where our rules come in that we're using here. Again, guys, when you're doing your work for your homework tonight, I highly recommend you actually go through your work, but show the calculations on the side. Don't use a calculator and just say, well, what's 3/6, what's 1/3 minus 4/3? You're going to get 0.8. You're going to get 0.8125 here as your number. That's not, I mean, it is the same as 1/12, but you don't have to necessarily know that. So show all these steps along the way. Okay, show all those steps. Your homework tonight is to do the front side of this worksheet, please. Front side only. Back side we'll do tomorrow night. We're going to work with these problems tomorrow during class. They're a little bit more complicated. Again, front side only, please.
Mr. Howell, oh my No, we're gonna have this debate from
Please take a few moments to gather your materials, clean up, and prepare for
I do that.
Also, the procedure is to have a very good birthday. Tomorrow, let us wish a belated birthday to Nancy and let us
Guys,
The study program would like to remind all
lower our voices so we can all hear
turn in
this.
timesheets for the days that they made up over spring break. Those who do not get the timesheet by Friday will be fined $160. All students participating in international night please see Mr. Blanco immediately after school today. That's all students participating in international events, see Mr. Blanco today after school. James Contreras, Isao Martinez, and Jose Zamora, please see Mr. Blanco at dismissal.
Yeah, that guy.
As Stingley, please see Ms. Nara outside the teacher workroom after school. Senator Colonel Gus, please see Ms. Keller in room 206 after school. Kathir Omar, please come to the front office after dismissal. Leon Enriquez, please see Ms. Torcios after dismissal. Gloria Giesbert, please report to the corporate work study office after dismissal. Mackenzie Bevar, Swan Johnson, and Khalil Rhodes, please all see Ms. Kerrigan after dismissal. Alvin Flores, please also come to the front office after dismissal. Mario Lindecker, please come to the front office to pick up a message. Attention ninth grade girls, Girl Power is coming to DVCR on April 25th. Did you get the letter in the mail last week? Dinner and workshop just will be held, but you have to reserve your spot. You have to stay so make sure you let the coroner know if you and the adult female will be attending. I guess presenters are excited about
With the concept